Hello, everyone, and thank you for attending today's webinar, Ethernet or EtherCAT for Motion Control, Choosing the Right Network for Your Applications. We would like to thank our presenter, Matt Clint from Galil, for being here today. I'm Leslie Langnaw, and I'll be your moderator. Just a couple of housekeeping details before we officially start the webinar. You will see several boxes on your desktop. All of these can be moved around to suit your preferences. Initially, the Q&A box is at the lower left. This is where you will enter questions for the Q&A session after the presentation. Another box to note is the additional resources box. It's initially at the lower right-hand corner of your desktop. This has resources, websites for you to go for more information or if you have additional questions that we can't answer. We also have a tweet box on the desktop, making it easy for you to tweet any interesting points as you listen to this webinar. You'll see that there's a list of hashtags already there for you to use. Now I'd like to introduce our presenter. Matt Clint joined Galil in 2013 as an applications engineer. Before coming to Galil, he worked as a development engineer in the physics department at UC Davis, where he was involved in developing hardware and software solutions for experiments in condensed matter and astrophysics. Matt has brought this experience to Galil and has worked with many research institutions on motion control and data collection projects. At Galil, he has worked closely with other application engineers and R&D on development of Galil's EtherCAT compatible controllers. Matt holds a BS degree in physics from the University of California at Davis, and he will be available at the end of the presentation to answer any of your questions. So without much ado, Matt, go ahead and take over the mic.
All right, thank you, Leslie, and welcome everyone to EtherCAT or Ethernet for Motion Control. As I said, my name is Matt. I'll be presenting today. I've been with Galil for about 2.5 years, and as Leslie mentioned, have been very much involved in development of Galil's line of EtherCAT hardware. Today, I'd like to lay out in pretty broad strokes both the Ethernet and EtherCAT communication protocols and detail what types of applications can benefit most from their use. In addition, I'd also like to talk about Galil Motion Control's EtherCAT 50,000 EtherCAT master and 57,000 EtherCAT I/O module. And then we'll go through some examples of using the Galil EtherCAT master with supported drives. And then finally summarize the advantages of costs of an Ethernet versus EtherCAT network. So first, a little bit about Galil. Founded in 1983 by Dr. Jacob Tal and Wayne Barron, and was the first company to introduce microprocessor-based digital motion controllers. We also pioneered the technology for controlling servo motors with only the position feedback, removing the need for tachometers. Today, Galil offers its 5th generation of motion controllers with a 32-bit RISC-based microprocessor combined with Galil's custom ASIC to solve the most demanding applications. As a pioneer in the industry, Galil introduced the first Ethernet-based motion controllers in 1999 and have shipped over 100,000 motion controllers in the industry that communicate via TCP and IP. Galil has been developing and selling motion and I/O controllers worldwide for 30 years and has built an established reputation as a leader in the motion control industry and automation industries. Our primary goal is to provide customers with the best products, services, and value while providing solutions to customers' needs. Towards that end, we work hard to ensure that controllers are feature-rich enough to cover most applications' requirements. To a large extent, most customers find that our standard products are more than capable of meeting their applications' requirements. But that being said, we pride ourselves in our ability to work with customers on custom hardware and firmware that meets specific needs. Commitment to customer support and education is the driving force behind our applications engineering department. With more than 100 years of collective experience, the applications engineers offer expertise in various fields, including electrical, mechanical, mechatronics, computer science, and my favorite, applied physics. So first, a brief overview. In the context of which we'll be speaking about Ethernet and EtherCAT today is motion control. And so a quick overview of motion control system. wherein you have a motor essentially to be controlled in an application. As encoder feedback, which is then fed into a PID loop, which then outputs a control signal to an amplifier that provides a corrective action to minimize the error between where the profiled motion is to be and where the encoder lists position. Standard or current technology uses an analog signal, so the control signal and feedback are primarily what we'll be speaking about today. Standard control uses either an encoder feedback or analog feedback for position information, and then an analog control signal to the amplifier, typically plus or minus 10 volts, which is then translated into a current, a torque in the motor, etc., etc. The benefits of this control scheme is that it's an established technology, decades of work behind it, very well understood in the industry. Low cost due to a variety of sizes, ratings, and vendors. There's quite a competitive market out there. And extremely low latency. The signals produced by the controller and encoder are essentially seen instantly. As soon as the motor control or the motion controller puts out that 10 volt signal, the amplifier sees it on the wire as fast as the electrons can move, which is pretty fast. Downsides: analog signals are susceptible to noise. Even digital encoder signals can fall victim to noise in extreme cases. There are ways to mitigate this: cable shielding, differential signals, but analog signals will always be susceptible to some sort of noise. Wiring between multiple components leads to an increased risk of failure and grounding concerns. In order to share the same voltage reference, they all have to be grounded together, which exposes you to ground loops, many other concerns. Wiring over long distances becomes problematic. Signal strength drops and becomes noisier. It's easier to pass a voltage across 5 feet of wire than 50 feet. You have to start taking into account wire resistance and things like that. And changing out an amplifier, a motor, involves low-level concerns. You have to think about circuit compatibility. Can this encoder drive this line driver? What's the impedance of the amplifier input? And all of that. Nothing that your standard electrical engineer isn't going to know how to do, but it is another concern. Now, digital control of amplifiers involves essentially taking that motor command signal. Instead of an analog signal, now you've taken that position or torque data and you've wrapped it up in a communication protocol, whether it be TCP, RS-485, Modbus, DeviceNet, or EtherCAT. Communication these days has become fast enough to make Ethernet communication virtually deterministic, meaning as soon as that packet is sent, it's received and processed. I say virtually because there still is going to be a delay, a communication delay, but for the purposes of an application, as long as that delay does not add latency to the system, it shouldn't be a problem. Benefits of Ethernet: easily upgradable. You can take a component out, plug another one in, plug the Cat5 Ethernet cable in, you're good to go. Simplified wiring, since only one communication line is needed. And the communications hardware can be very noise immune with differential signaling and shielding. Downsides: because every node on a network, so every amplifier, every controller, every I/O module, has to have its own microcontroller, essentially an onboard processing unit that can take that data coming out over Ethernet and pipe it to the hardware. And this does, and as mentioned before, this does introduce some latency, but depending on the system, this may be an issue or not. So in the two systems that we're going to look at today, both motion control systems, but different ways of addressing different applications. So in the first scheme we'll talk about is centralized control. And this is something that's akin to, say, a CNC machine, a diagnostic machine, semiconductor robot, something where the motion controller, the motors, the amplifiers, any control HMIs or PCs are all contained in the same box, essentially, or on the same desk. Motion commands are relayed to the drives via analog voltage reference, as we referenced before. And motion profiling and the servo loop are all handled on the motion controller and hardware. As we mentioned before, the only latency is due to how fast the electrons can move around, which is pretty fast. So with that, you get a high degree of determinism. And because of that, motion can be synchronized and coordinated with changes in I/O states very quickly. So, you know, we're talking nanoseconds. So as soon as an I/O toggles, the controller can take appropriate action based on that hardware change. Again, because this technology has been around for decades, lower cost. Typically, the motion controllers and the amplifiers will be lower cost. And again, tightly coupled motion over multiple axes is pretty industry standard with this kind of hardware. Alternatively to centralized control is the distributed control. Pardon me. Distributed control scheme. And in this scheme, essentially, we can think of it as the left hand doesn't know what the right hand is doing. You have a central node, a master node, and think of something like a power plant control and monitoring station. Something like that, you have PLCs and motion controllers that are scattered throughout the factory or the plant, and they're all reporting back to this central monitoring node, which can have multiple screens, multiple buttons, ways of controlling the plant. Benefit of that is that you can have everything run from one control room. The downside to that, because you are using Ethernet, is the lack of determinism. So essentially, the time and rate at which each component communicates with the master is variable. And so if you are looking to execute some movement on one side of the factory floor based on the input read on a PLC on the other side of the factory floor, depending on how tightly those need to be coordinated. Do you need that motion to be coordinated down to 1/10 of a second, or will a few seconds work? Can it be plus or minus? So real-time data has to be collated on the master using timestamps. Essentially, every PLC or motion controller, when they send information back to the master, there's a timestamp on it that the master then sorts through and figures out what came in where and how to best take action. So how do Ethernet and EtherCAT fit into these? Quick overview. So Ethernet's main advantages are that it's flexible, high bandwidth, non-deterministic, in that it stresses flexibility, designed to move large amounts of data through many different nodes. I mean, we're talking billions of addresses. Most of the traffic on the internet is Ethernet, TCP. So it does a whole slew of things well. Stresses flexibility. Communication is straightforward on the surface, but has been worked on for decades by a lot of smart people, so there are many layers of abstractions to wade through. But the basic premise is take some data coming from one address, would be the IP address of a server somewhere, and send it to another address, the client, using either TCP, UDP, whatever the mode of transmission is. And so it's very open-ended, very flexible, which it needs to be. The types of data that are transmitted over Ethernet, TCP, UDP are very much varied. And so the means of encoding that data, the means of moving that data and interpreting it also needs to be rolled up in that Ethernet packet. There's a lot of overhead, but the benefit of it is, again, that flexibility. EtherCAT. An EtherCAT frame is very similar to an Ethernet frame, except that it's been very much optimized. EtherCAT trades flexibility for speed, essentially. So EtherCAT communication uses standard Ethernet hardware, Cat5 cabling, network interface cards, and the speed comes from the fact that on an EtherCAT network, the master that's coordinating the EtherCAT communication already knows where it's sending data. And so the EtherCAT packet does not necessarily need to have addressing information and that needs to be interpreted or causing latency due to processing. So before an EtherCAT network can function, both the slave and the master have to agree on where and when each byte is transmitted. A little bit of there's only a few differences between an Ethernet frame and EtherCAT frame on the surface of it. As you can see, the Ethernet frame is a header, data, and a CRC. CRC is error checking. So in the Ethernet header, you'll have two fields. One is a source address. One is a destination address, just like a letter you put in the mail. Where is it coming from? Where is it going? The Ethernet data can really be anything that you want to be sent, whether it be ASCII or binary data or hex encoded values. It's pretty open-ended. An EtherCAT frame is a subframe, essentially. So you still have your standard Ethernet frame with an Ethernet header. However, the addresses, the source address and the destination addresses are now different than an Ethernet frame. The source address remains static. The destination address is now broadcast. It's sent to the EtherCAT frame is sent to every address out there. It's a 6-byte address. That's quite a few nodes to send to. Then there's an EtherCAT header, essentially telling any hardware out there that this is an EtherCAT frame. If you're not an EtherCAT node, don't pay attention to it. And if you are, here's how you interpret it. EtherCAT data is then contained in the frame, followed by working counter and a CRC. EtherCAT communication based on CAN open. For the purposes, the EtherCAT standard encompasses a lot of different communication methods. For the purposes of this webinar, we'll be focusing on CAN open over EtherCAT, which is CAN open is an automation network protocol. So we'll be focusing on CAN open over EtherCAT, or COE. Again, uses standard Cat5 cabling and Ethernet network interface cards, and features high bandwidth communication up to 100 megabytes per second, or megabit per second. Minimal latency due to hardware processing. Instead of a microcontroller or a PC on one side or the other of the network, you now have dedicated chips, FPGAs or CPLDs, that take the data from the EtherCAT packet and map it directly. So you no longer have software sitting somewhere interpreting and addressing and unpacking and repacking data. It's all done in hardware. Minimal latency. In a motion control context, what is the data that's being sent over EtherCAT? You're seeing data specifically sent from a motion control master to, say, an EtherCAT drive, so a amplifier and motor, and you're specifically sending position, velocity, or torque information to that drive. And for I/O modules, you're looking at digital or analog input and output. Drives are typically assembled in a daisy chain topology. So you have your EtherCAT master wired directly via Cat5 into your first drive, which then has a 2-port Cat5 switch, which then runs to the second drive, and so on and so on and so on. And one of the more popular analogies for EtherCAT communication, how it works, is the data train. Essentially, an EtherCAT packet comes down the cable, down the line, and each drive, as the train comes through, the drive takes information off. The information that pertains to it takes it off and puts its current status information on the train. And the train zips down to the next drive, and so on and so on and so on, turns around, comes back to the master. Master interprets that data and calculates new data to be sent out. And this happens on a periodic deterministic cycle. The means of coordination for EtherCAT communication. The meat of EtherCAT coordination is distributed clocks. How does EtherCAT get around the non-determinism of an Ethernet network? And so the distributed clock implementation involves, when the network first comes up, the EtherCAT master determines how long it takes, and this is in nanoseconds, for a packet to get from the master to each slave. When that network is first brought up, 20,000 of these packets are sent between the drives in order to calculate a very high resolution timestamp. Again, nanoseconds. And so the master calculates these offsets and it assigns a time offset to each drive. Once the network is up and drives are communicating with the master in real time, every cycle the master sends out a sync pulse. And this pulse, when the drive sees, each one of the drives on the network sees this pulse, it will take whatever information, position or torque or velocity information it is currently received from the master, and will execute it. And so in this way, each drive starts motion on the same at the same moment in real time, regardless of the communication latency. And so where this really comes in is in what's termed cyclic synchronous communication between the EtherCAT master and the EtherCAT drives. In this method, the EtherCAT master every cycle time, which can be anywhere 10 milliseconds down to multiples of tens of microseconds, will send out position or torque or velocity data depending on which mode of motion you're using, and then send out the sync pulse. In cyclic synchronous position, the EtherCAT master, all it sends is position. It's a 4-byte piece of data, and any PID profiling is handled on the slave. So the controller simply says, go to this position, and when I come back at the next cycle time, tell me where you are. I'll tell you where to go next. Similar with velocity, except the data being sent now is simply velocity profiling to the drive. In torque mode, the EtherCAT master handles the PID control and then sends torque values directly to the drive. So how is this data transmitted or sent from the master to the slaves? Again, for the purposes of motion control, EtherCAT is used to relay data between a master and the slave nodes on the same network. Each slave includes a series of spaces or registers in their memory to which the EtherCAT master can write to and read from. So every EtherCAT slave, whether it be a Yaskawa or a Beckhoff or a Panasonic or a McCapian or any other number of EtherCAT vendors, every one of them has a spot in memory to which position information is dedicated. So an EtherCAT master can connect to an EtherCAT drive and send a number to that register. The EtherCAT drive will then interpret that as a position command. And this area of memory in these EtherCAT slaves is referred to as the object dictionary. And as mentioned, is identical across all EtherCAT slaves. That's what makes EtherCAT EtherCAT. And these registers include digital I/O status, analog I/O status, position, velocity, torque information, drive status, whole slew of information in there. So before the network is brought up, master builds the packet structure, essentially telling each drive, tells each drive where to look in the EtherCAT packet for its information. So say the first drive on the line is told, here's the incoming packet, look at the first 18 bytes in it. And the first 2 bytes will be this. The next 4 bytes will be that, and how to route them. So the next 4 bytes will go to that position register. The next 4 bytes will go to the digital output register. And then once the drive receives that sync pulse, now it executes those commands. There's a simplified diagram of how EtherCAT data is sent out on every cycle. So you can see the master is uploading information from the previous PDO and then downloading new information into the outgoing PDO. It goes by the first slave, which then exchanges data with only the first piece of the PDO there. Comes through, the second drive now exchanges data with the second piece of the PDO, and then so on the third and fourth drive. And then the PDO returns to the master to start the cycle all over again. Again, this happens on the distributed clock cycle, which, as mentioned, can be milliseconds to multiples of microseconds. A little more fine-grained idea of what the PDO will look like. This is an example from our EtherCAT master, the information that we will send back and forth to the EtherCAT drives on the network on every cycle. And so each drive sees a control word which tells the drive whether to servo the motor, number of different servo or turn off the motor, number of different functions. Target position is pretty straightforward. Tell the drive what position to be at in encoder accounts. And that's it. That's all the master sends out to the drives on every cycle. That's one of the reasons that EtherCAT is so streamlined. You're sending such a small amount of data, which is then interpreted on the other end. So the PDO that goes out is then, so the first two fields there are received by the drive, and the drive then places 3 pieces of information in that PDO. Interestingly, the drive or the EtherCAT slave does not change the size of the packet at all. When the packet first comes out from the master and goes to the slaves, the encoder position, digital input status, and status word fields are all filled with zeros, just placeholders. As the PDO goes to the slave then fills those fields with its information while at the same time taking its control information from the PDO. And then as referenced here, this happens for each drive on the network when it comes back to the master. And so in this way, really the servo loop of the controller, the controller, instead of running everything in a localized box with analog signals to amplifiers that are 2 feet away, now servo control can be spread out across, as previously mentioned, across a factory floor. So an example of an EtherCAT network layout. Here you have an EtherCAT master, which is then communicating with each EtherCAT drive or I/O module on the network, giving position or velocity or torque commands to each drive. On the right, we have just a simple diagram of how that wiring occurs, even the Ethernet cable between each RJ45 jack. And one of the benefits of EtherCAT is the scalability. As long as the master will support it, the EtherCAT standard currently includes the capability of running up to 2 to the 16 drives, which is near 65,000. To my knowledge, there are not any applications that have implemented that yet, but the capability is there. So everything that we've seen with regards to communication would simply be scaled up. Put more PDOs into the EtherCAT data, or send more packets with more PDOs in it. Previously mentioned that each EtherCAT drive will only see the data that's addressed to it specifically, and forwards everything else through. And so really the limitation is really how fast can the master build the profiling information and send it out. So in contrast, here's an Ethernet layout where you would typically have host PC or HMI, or that control center as referenced before, working with a motion controller. So over Cat5 is now communicating with the motion controller. The motion controller is then communicating with the drives via analog control reference voltage, or a step and direction if it's a stepper, and then relaying that information back to the PC. But the deterministic real-time motion is being handled on the motion controller as opposed to the PC. And again, that is specifically because Ethernet communication is not deterministic as opposed to EtherCAT. Speaking of EtherCAT masters, a year and a half ago, Galil released our DMC 50,000 EtherCAT master, which includes all the features of our flagship DMC 4000 series, but adds the capability of communicating with up to 8 EtherCAT drives in cyclic synchronous position mode. And so, as previously mentioned, in that mode, the 50,000 calculates positions for each drive to be at on each cycle, and then sends those out, which the drives then execute. At this point, it's the only motion controller in the industry with the ability to mix and match local and EtherCAT drives. So in the case of the 50,080, let's say, 8 axes of control, up to 4 axes can be local, so standard analog drives, and those can be servos or steppers. And then the second 4 axes, the second bank, are EtherCAT only. And it gets a little confusing. The number of you can have up to 8 EtherCAT axes, or 4 local and 4 EtherCAT, or 2 local. The confusion comes from the flexibility, and it is all configurable in software. You can replace a local axis with an EtherCAT axis with two commands. That speaks to the configurability and compatibility. If you have an existing application on a Galil DMC controller, adding an EtherCAT drive to it is really a matter of 4 or 5 commands, and requires really no knowledge of, well, what we've been talking about here. Setting up PDOs, communicating with the drives directly, setting up your distributed clock. All of that is all handled on the EtherCAT master, the 50,000 EtherCAT master firmware. At this time, there are multiple drive vendors supported. We have a list of those a little bit later here. And the 50,000 is also compatible with Galil's entire line of internal servo and stepper amplifiers. There really is just a ton of versatility there. You have access to the internal amplifiers. You still have access to external third-party analog drives, as well as EtherCAT drives. And so it's really meant to be a jack of all trades. Recently, we released our EtherCAT I/O module. So this is going to be an EtherCAT slave that's on the network that would be communicating with the 50,000 or any other certified EtherCAT master. Our EtherCAT I/O slave has been conformance tested, which means that it's essentially the seal of approval by Beckhoff. They've tested it and confirmed that it does function as spec'd with EtherCAT masters. Supports distributed clock. The analog I/O ranges are programmable from 0 to 5 to plus or minus 10 volt, and comes with field upgradable firmware, as opposed to needing to send it in to be upgraded. Firmware can be easily downloaded from our website and then uploaded to the controller using our standard communication software. All RIOs come standard with 16 high power, 500 milliamp sourcing, opto-isolated digital outputs, and 16 opto-isolated digital inputs. There's an option for 8 analog inputs and 8 analog outputs. If using a 50,000, DMC 50,000 EtherCAT master, commanding movement on a local axis versus an EtherCAT axis is pretty simple. So on the left we have an example of the commands necessary to issue to any DMC controller actually, but in this case we'll talk about the 50,000. So for a local axis, you energize the motor with SH, servo here, order a relative move with 1,000 counts, order begin motion, wait for motion to complete, that's the AMA. After that, set a digital output to indicate that the motion is complete, and then message to the terminal that the motion is complete. And if we look to the right, where we're now using an EtherCAT axis for that same motion, we see that the 6 commands have been rolled into the center there. And in order to switch out a local axis with an EtherCAT axis, you simply set a motor type. Motor type of 10 in this case indicates bring up the A axis in EtherCAT position mode. EX says take the first drive that's on the line and substitute that for the A axis. IO says take the second node on the line and assign that as an IO module. So in this network we would have one EtherCAT drive and one EtherCAT IO module. And then EU1 brings up the EtherCAT network. Now you're up and running. You are sending the DC sync pulse as well as the position information back and forth. And the 50,000 cycle time is 1 millisecond. So every 1 millisecond, you're updating the position registers on those drives. So again, servo here, PR. Now instead of this motion happening on your local axis, you're going to see that motion on the EtherCAT axis. And then the commands after here, set bit 11,001 means set the output on the IO module, which in this case we're using a RIO. So set bit, set the analog or send the analog input to the terminal, set an analog output, clear bit. It's all pretty straightforward, pretty transparent, and really by design. The driving force behind Galil's EtherCAT development is ease of use, much like most of our product philosophies. And so, if you're not necessarily interested in the intricacies of motion control in EtherCAT, you have a machine that you're building, and you need to execute a certain amount of motion in a certain amount of time. Use these commands, and you're up and running. Example of a DMC 50,000 hardware layout, and this is really kind of the kitchen sink, showing the capabilities of the 50,000 across multiple platforms. So in this case, we have 3 EtherCAT drives with servo motors, a RIO 57,000 for EtherCAT IO. So that's your EtherCAT network working there. On the right, the servo motors are controlled via plus minus 10 volt control signals, and then the stepper drivers are controlled via step and direction, so TTL step and direction lines. And this is perfectly feasible for a controller or for an application that needs both centralized and distributed control. This is going to do what you need. List of compatible drives so far. With the 50,000, we've included little under 10 drives, as well as 2 I/O modules, both VIPA and the Galil RIO 57,000. And for the most part, we've chosen these drives the broad spectrum of the market. One that we have found customers that we have worked with have the most interest in integrating for support. If you're considering using a Galil DMC 50,000 or a RIO, 50,000, and you don't see one of these drives does not meet your requirements, please contact us here in the Application Engineering Department, and we can work with you to discuss adding support for a drive. And so, in summary, EtherCAT protocol is becoming, more and more popular, getting a lot of traction as an efficient solution to large-scale automation applications that require real-time distributed control over long distances. And those are really the key words. Does your application need real-time distributed control, say, again, across a factory floor over long distances? If it does not, if it is a local application, again, CNC machine, something, if it's all in the same box, it's all in the same cabinet, if the drives are even within 5 or 10 feet of the controller, an analog solution is most likely still going to be the most cost-effective for those requirements. And really, that's because, as mentioned, in EtherCAT, each controller, each drive, has its own microcontroller, has its own current loop. There's quite a bit of control software and hardware on there. But this can be offset in some cases by the ease of wiring. It is just a Cat5 cable back and forth. But because of that, Ethernet communication and analog drive control will continue to be the most cost-effective for applications that don't need a distributed control layout. Lastly, if the application could need either or, the design goals are still a bit vague, why choose? Again, with the DMC's 50,000's ability to mix analog EtherCAT drives or stepper drives, whatever you need, you're not automatically locked into one or the other, which grants a huge amount of flexibility for those first looking to, I'd say, take first steps into using EtherCAT in applications. So, thank you for attending today, and I hope you found this presentation insightful. And I'd like to thank Leslie for their support and assistance. And at this time, I'd like to open up the presentation and take any questions you have regarding.
All righty. Thank you, Matt, for a very informative presentation. And as Matt said, now is the time to enter in your questions into the Q&A box that's on your desktop. And first of all, okay, here's one that's come in. Are there plans for a 1 gigabit per second Ethernet or, well, there is Ethernet, EtherCAT communication in the future?
To my knowledge, no. However, I'm not involved in the development of the EtherCAT standard. However, at this point, really the mitigating factor for EtherCAT communication is how fast that EtherCAT master can put information out. And so, if the EtherCAT master is not doesn't need to put out gigabytes per second of data, then there was really no need to move to that yet.
Okay. And let's see here. How about with wireless routers and adapters in a motion control system? Can you use these with either Ethernet or EtherCAT?
So, and that's actually a great question. That's an important point. As we said, EtherCAT packets are kind of a variant of Ethernet packets. That being said, specifically because EtherCAT packets are broadcast to every address. In the Ethernet header there, the source address is static, but the destination address is anything and everything. As soon as that packet hits a switch or a router, whether it be wired or wireless, the router looks at the destination address and says, oh, send it everywhere. So it sends it everywhere. And now you've got packets bouncing every which way, back to the master, back to every other slave on the drive. And so, long story short, is that standard Ethernet hardware like routers, switches, hubs, wired or wireless, are not compatible with EtherCAT. Ethernet, absolutely, those are going to be, Ethernet communication is going to be absolutely compatible with it. That's what they're for. With the caveat of in motion control, wireless is still an emerging technology. The downside of wireless is if a node on a wireless network doesn't receive a packet, how does it know it didn't? Now granted, in TCP you have sinks and ACKs, but then if a packet is missed and a retransmission is requested, now you've added latency to the system. And so wireless on the face of it is going to be compatible with Ethernet motion control, but there are an awful lot of caveats involved in it, and so a hard cable is still going to be the best way to go.
Okay. Can you briefly summarize the differences between EtherCAT and Ethernet?
Sure. Yeah. In a nutshell, EtherCAT is great for, as mentioned, real-time distributed control. So if you need to control servo motors and I/O or steppers across a large physical range, and again, I keep using the example of a factory floor because it's really where it shines here. Then EtherCAT is really something you need to look at. Ethernet communication would be specifically between an HMI or a PC and a motion controller, which is handling the real-time motion. And so it really is, again, it's a question of the application for which one is better.
Okay. This is a question. This person didn't hear whether or not you mentioned the redundancy gained by daisy chaining from the master to the slaves and back to the master again. Can you talk about the benefits offered by this architecture?
Yes, some EtherCAT masters implement what's called EtherCAT redundancy or a ring topology. And so in the examples that we've covered, it's one Cat5 cable runs from the master through each node. And so then the PDO goes down the line to the last drive. The last drive sends it right back down the same cable. In a redundant network, there's now two Ethernet cables running from the master. So it runs over one Ethernet cable runs from the master to the first drive, and then and then subsequently daisy chain, just as we would with a non-redundant network. But then the last drive has an Ethernet cable that now runs back to the master as well. And so the benefit of redundancy is if one of those cables is inadvertently snipped or loses connection, the other cable picks up communication seamlessly, ideally. And so the benefit in that is going to be, redundancy for safety concerns. If there's a reason why that cable gets clipped. However, most EtherCAT drives, as part of the standard, do have, especially in synchronous modes here, even if you're not using a redundant network, if the drive doesn't see one of these sync pulses or position update information, it immediately assumes the network has gone down, and most drives will immediately go into a safe off condition where they turn the servos off.
Okay. And another question that has come in is this person is already using a Galil Ethernet-based controller for a 6-axis application. Should they consider moving to EtherCAT-based controller?
Good question, and a question that we very much like to hear in applications here. Before going to our website and straight placing an order for 50,000 because it says EtherCAT on it, we very much prefer to talk before that, because we have very little interest in selling people things they don't need, and so we really like to discuss, is your application working now successfully with analog drives? And if so, are you looking to expand it in ways in which it would benefit from EtherCAT? Yeah, that's really the driving force behind it. Give us a call here, and we can talk about whether or not your application can benefit from EtherCAT, including the increased cost of drives. I mean, an EtherCAT drive can run anywhere from $1,000 to $5,000 in some cases per drive, as opposed to Galil's internal local drives for a set of 4 of our sinusoidal commutated drives. It's $1,000 for 4 axes, and so really the cost starts to come into play when we're understanding whether or not we should use EtherCAT or not in your application.
Okay, this is an interesting one. Is a hot connect node available in motion control?
I'm sorry, a hot connect node?
Yeah, hot connect node. I'm assuming they're talking about being able to pull boards in and out without shutting down the system.
Okay. Well, so by the nature of that EtherCAT network, especially when running in a distributed clock fashion, if any of those drives are unplugged, any other drive down the line now no longer sees any of that information and will shut down. As to how that's implemented with a redundant network, I'm not sure. If this is, I would certainly encourage them to either send me an email or give us a call at your applications, and we can talk about it a little more. But to my knowledge, that feature hasn't been implemented.
Okay, and here's another question about this person has a combination of electrical and hydraulic servos, along with a couple of axes with step motors. How does EtherCAT address this connectivity?
Mm-hmm. So, yeah, one of the nice things about EtherCAT is that whatever is being controlled on the other side of the amplifier, so you have your EtherCAT slave amp sitting on the network, the EtherCAT master is sending it. If you're in cyclic synchronous position mode, the EtherCAT master is sending it a 4-byte number every cycle, and that's it. And so interpretation of it is left up to the drive. And so the drive takes that position, and whether it be a hydraulic servo or a stepper or who knows what, whatever is on the other side of those amplifiers is going to be transparent to the EtherCAT master, to the controller.
All righty, great. Okay, well, thank you everyone again for attending this webinar. Thank you to Galil and to Matt for presenting it. Just a couple of reminders here. We will be sending out an email link to this webinar in a little bit, and it will also be available on our website at designworldonline.com. You can continue tweeting about it. You can also connect with us on Facebook and LinkedIn and any of the other social media venues. And if you're interested, you can also continue any discussions you may have on our own sort of Facebook-style social media platform called engineeringexchange.com. So again, I'd like to thank everyone for attending, and thank you again to Galil and to Matt for presenting. Have a great rest of your day.